We're going to start a brand new unit on chemical bonding, and it's going to be great. So, first, to understand chemical bonding, we really need to be understanding and being able to be familiar with our valence electrons. So, a valence electron is the electron that's on the outside of the furthest most on the outside shell. So the one farthest away from the nucleus, or the energy level farthest away. So to find the valence electrons, you were taught this in middle school, but it's very easy to get, is if we have carbon right here, it is going to be in the number of electrons in the outermost shell. So the outermost, we start a new shell at each row, at each row on the periodic table. So that's simply the number of elements it is over. So if this is 1 valence electron, 2 valence electrons, 3 valence electrons, and 4. Okay, so carbon has 4 valence electrons, and then nitrogen will move 1 over, and that has 5, and then we'll move 2 over, and in this column right here, this has 7 valence electrons. So you'll essentially just see that in this first column is 1, 2, 3, 4, 5, 6, 7, 8. If you ever get asked, the transition metals, they vary. They always have at least two, all of them. So aluminum has going to be 3 valence electrons. That's because it's right over here. And then potassium is right here, so it's in the 1 valence electron, and calcium has 2. So you should be responsible for that to understand your valence electrons. So now we can take those valence electrons and draw them. So if we take chlorine and it has 7 valence electrons, we're going to put 7 dots around it to do an electron dot structure. What we do is we're going to put a single dot here, single dot, single dot, single dot, and then keep going until we pair them all up. So what you seeing here is that you have a maximum total of 8 right here, but since we have 7, we're going to have 1 single electron right here. So for rubidium, it only has 1 valence electron, so we just put 1 dot. Magnesium has 2 valence electrons, so we put 2 dots. Sometimes you will see a 1 dot here and 1 dot here to represent the 2 electrons that are paired together in the s orbital, but 2 dots like that is fine. Now, phosphorus has 5 valence electrons, so we would pair it like this. So we'll pair up single electrons first, and then we will start to pair up the second ones. So that's the way we write that. That is the recommended way, and because electrons don't like each other, they're not going to pair up unless they have to. And now for krypton, it's a noble gas, and it has 8 full valence electrons, and it has a full outer shell, and aluminum has 3. Okay, each of them with single electrons. So now looking in your notes, this is straight off the notes. A chemical bond is an electrostatic attraction between the nuclei and the valence electrons of different atoms that binds the atoms together. Okay, so that's for all chemical bonds. We're going to look at a couple different types of bonds. Now, the reason why atoms bond is because of the octet rule. They're trying to fill up 8 valence electrons, and everybody is trying to get has a race to 8 valence electrons. So each atom will either gain or lose or share electrons until it has an octet of valence electrons. It always wants 8. Okay? So to achieve this, we can do it a couple of different ways. We can do an ionic bond, which is a chemical bond that results from the electrical attraction or electrostatic attraction between a large number of cations and anions. Remember, cations are positive and anions are negative. This type of bond forms between a metal and a non-metal. Now, atoms bonded together by ionic bonds gain this configuration by gaining electrons. The non-metal will gain an electron or 2, or losing electrons. The metal will give an electron or 2 or 3. So here's a good example. We have potassium. It is a metal, and it only has one valence electron, and then chlorine has 7 valence electrons. So potassium would actually like to get rid of an electron, because if it does, then it's going to be left with this core shell that's not pictured. Its core electrons that it has are going to be full, considered full now. So that would be really great for potassium. And now chlorine, it would be really great for potassium to actually gain an electron. So everybody wins, essentially. So potassium will give up its electron. So we show that with the arrow right here. We draw the arrow in the direction of electron transfer. And then we end up with this. Now, I know it's a little blurry. Hold on. It's going to come back. It will stabilize in a second. So we see that chlorine has its X's right here. We represent the X's as original chlorine electrons. And then this electron represents an original potassium electron. Now, this actually implies that there is a covalent bond here, so I'm not really in love with this picture, but that is essentially what is going on. So we can show them like this. If we have calcium, it has 2 valence electrons. And if it's bonding with chlorine, chlorine can only accept 1 valence electron. So we'll actually need 2 chlorine atoms for every 1 calcium atom. So we'll get to this later, but that's why calcium's formula is going to be CaCl2. Okay? It's going to have 2 chlorines in it for every 1 calcium. So we'll get to the naming and stuff later. But this guy is the cation because he's positive. He's the metal. The metal is always positive. And then the anion is negative, and that is the nonmetal. Okay, so it works out that way. Now, a covalent bond results from the sharing of 2 electrons between 2 atoms. This type of bond forms between 2 nonmetals. So the sharing of 2 electrons, what happens is one atom will contribute 1 electron, and then the other atom will contribute another electron, and so now they have 2 electrons kind of stuck in the middle, and that means that these 2 electrons here are the chemical bond. Okay, so this is one way to show that in a water molecule. Water is H2O. Here we have oxygen. We have its core electrons and its valence electrons here. And so 1 electron was originally from oxygen. This electron was originally from hydrogen. And the same thing over here. So now oxygen has a stable octet, and then hydrogen is filling up its duet. Okay, hydrogen does not fulfill an octet. It only needs 2 electrons to fill it up because that first energy level is the 1s or energy level, and there's only takes 2 electrons to fill that one up. So here's the same story with methane. We have carbon, and you could tell that carbon's original valence electrons are the 4 blue ones, and then hydrogen contributes 1 electron each. So we get 1 carbon and 4 hydrogens, so that would be CH4 or methane. Now the other type of bond is the metallic bond. Now it is formed by the result of a sea of mobile valence electrons. I know this is not in your notes, but what this is these are positive cations here. These are the metals. These are the actual atoms, the nuclei, and they're all positive nuclei, each one of them. And then what they've done is they've contributed their electrons kind of to the group, and you can see the electrons whizzing around in constant random motion. Now this is actually why metals conduct electricity really well, because they can pass electrons very easily from one thing to another. What the bond that's happening is the positive cation is attracting to the sea of electrons, and so they're squeezing closer and closer together. So another good static picture. So the big idea, if you hadn't figured out, is the objective of the atoms bonded together by ionic or covalent bonds is the same. It doesn't matter if it's ionic or covalent, the objective is still the same. The atoms desire the stable electron configuration of a noble gas. The noble gas electron configuration results in both atoms lowering their potential energies. So the idea here, good free response answer, is that we want a noble gas electron configuration, or a noble gas configuration. That is a octet. That is a full octet. That's a fancy name for it. So here's in your notes a little activity to practice. If we have an element here and an element here, and just by telling where they are in the periodic table, you should be able to tell if it's a metal or non-metal. We've gone over this before. If it's on the left side, it's a metal. If it's on the right side, it's a non-metal. And so determine whether all of these are metals or non-metals. So pause, and we'll start back in a sec. Okay, welcome back. So the potassium is a metal, oxygen's a non-metal, nickel's a metal, carbon's a non-metal, and then calcium is a metal. And hopefully you got these. How'd you do on those? Cobalt is the only metal in the second column. So when a metal bonds with a non-metal, what type of bond do we get? We get ionic. Okay, that's how that works. When a non-metal bonds with a non-metal, we get a covalent bond. When you have a metal and a metal together, you get a metallic bond. Okay, this would be what we would call an alloy. A non-metal would be covalent, and then metal, non-metal would be ionic. So you can really determine bonds, determine the type of bond just by where it is on the periodic table between two elements. Very simple, right? So you could also determine it by their electronegativity. So the degree to which the bonds are ionic or covalent can be estimated by comparing the electronegativities of the bonded atoms. The more two atoms differ in electronegativity, the more ionic the bond is between them. The type of bond that will form between two atoms can be determined by subtracting the electronegativities of two atoms involved in a bond. So an electronegativity is again described like a tug of war. You have your electrons right here, and you have your nuclei over here and over here. And so the higher the electronegativity, the more it's going to pull the electrons towards it. Okay? So they're competing for the electron, essentially. So the stronger the team, the higher the team's electronegativity, essentially. So, yeah. So up here, in that tug of war analogy, the ionic bonds have a big difference in electronegativity. The one of them has such a high electronegativity that essentially in the tug of war analogy, it's going to snap the rope, and it's going to pull that electron completely towards the higher electronegativity. And it is such a great difference. Now here, this is a lopsided difference. One team is obviously winning, but the rope is still there. It hasn't snapped. And then here is an equal balance between in the tug of war. So essentially right here, this is a good example. So if you have the low electronegativity of cesium and then the high electronegativity of fluorine, it's like the Navy SEALs in the third grade. The Navy SEALs are obviously going to destroy the third graders, and they're going to pull the rope completely towards that, and the third graders don't stand a chance. So essentially fluorine is stealing the electron, okay, because it's so electronegative. And that is exactly what this transfer of electrons is in an ionic bond, because this is a metal and this is a non-metal. Okay, good, because it's an ionic bond. Now, the thresholds for these are here. Now, this is a very generalized concept, but pause and copy this in your notes because it's going to be important for your assignment. But these are just approximations. There's no hard and fast rule, but you shouldn't run into any big problems on your assignments. So now what we see here is we have ionic, and we have polar covalent, and we have non-polar covalent. So a polar covalent is a bond in which the two bonded atoms share the electrons unequally. So what we have here is the electron cloud. The electrons are more likely to be around chlorine rather than hydrogen because chlorine is more electronegative. Now, in a nonpolar bond, the electrons are shared equally. So the electrons are more likely to be around both the two hydrogens, somewhere in the middle. They're just kind of circling around. So it's a good way to do that. Way to show that in a polar covalent bond. Way we sometimes denote this is using the Greek letter delta right here. That's a lowercase delta. And it says a partial negative charge. That means that there's mostly the negative charge, or the electrons are on this side, and then the partial positive charge, and the electrons are likely not on this side. Now, we don't show the partial charges on nonpolar covalent because there is no partial charge. So now, using those values, you're going to determine this, the type of bond that will form between the following pairs of atoms. Now, what we're going to do is we're going to skip ahead. In this page of your notes, you should have all the electronegativities of all the periodic tables. Note that the noble gases are 0, except for xenon. Xenon's a little weird. But we have potassium, we have bromine. So we're going to find the difference in their electronegativities. This is this is bromines, and this is potassiums. So it doesn't matter what order you do it in, just take the higher one minus the lower one, and we'll get this. Well, this one falls in the ionic range, the one that I showed you before, this range right here. So that means that it's an ionic bond. Essentially, you'll do the same thing for carbon and sulfur. You'll find the difference in electronegativities, and you'll find that it's 0.03. So if we look at our scale right here, it's going to be nonpolar covalent. And then for this one, magnesium and oxygen, we'll see that the difference in electronegativities is 2.13, so it must be ionic. And then hydrogen and oxygen, the difference is 1.3. So looking at our scale right here, 1.3 falls in the polar covalent range. Okay, so hopefully you'll be able to do that on your assignment pretty simply. Okie dokie. So if you are going to pause, here's your mastery check. Arrange the following pairs of atoms from most ionic to least ionic. So we're going to list all their differences in electronegativities here. So the most ionic one is what we're going to start with. So that's going to be potassium to oxygen, lithium to nitrogen, sodium to sulfur, carbon to fluorine, iron to chlorine, and then sulfur to oxygen. Okie dokie. So that's pretty much it. Yes. So one last thing I will say is that this one has the most ionic character. There's a thing that we can throw out there. This has the most ionic character, and this one has the least ionic character, as you might say. But that should actually take care of everything here. Yeah, that's just another mastery check. And so you have a little bit of homework. In Mr. Russell's class, you need to finish lesson 7.1. All right, have a great day.